By the end of this lesson, you should be able to identify, both graphically and algebraically, the phase shift of a sinusoidal wave and the vertical shift of a sinusoidal wave. We again start with some definitions. Phase shift is trigonometry's version of a horizontal translation, and it represents the offset of a wave from its standard position. Algebraically speaking, this presents itself as a constant that is added to or subtracted from theta. As functions of x translated horizontally due to a difference in the input x, our wave functions will also translate horizontally, here by applying differences to the input theta. Vertical shift is, as its name suggests, a vertical translation applied to the rest of the function, after all the other transformations have been performed. In shifting the wave function vertically, the baseline of the wave function is also adjusted by the same amount, as we'll see shortly. Algebraically speaking, vertical shift presents itself as a constant that is added to or subtracted from the function at its tail. For this graph, we're actually going to extend our axes through the origin, from -4 pi all the way to 4 pi. We're also going to set up our parent sinusoidal function in this hot pink that has come to be pretty familiar. And when I say parent function here, what we're implying is that this is the basic sine wave from which all of our transformations will stem. Now, phase shifts control only the lateral movement of the wave, with negative or leftward motion being represented by an addition to our input theta, and positive or rightward motion being represented by a subtraction from our input theta. In all such cases, the original sine wave is not scaled or compressed in any way. Its maxima and minima are just out of phase now. If we were to do something like shifting by an integer multiple of 2 pi, however, we would see that a wave being shifted by whole multiples of its own period remains in phase with itself. We're going to redraw our axes and clean up a bit to address vertical shift. This time, however, we won't need to extend our wave sideways quite so far. The important property that we're going to draw from for vertical shift is actually the baseline. If you recall from our previous work, the baseline of a sine wave without any transformation is the equation y equals 0. This can also be visualized as an addition or subtraction of value 0 on our parent function. From here, if we want to observe a vertical shift upward by some value, let's say 2 for example, we simply shift our baseline upwards by 2 spaces, adjusting our constant that is being added after the function. As we shift the baseline, the function itself comes with us. Remember, the baseline acts as a midline for the wave function, so the extrema on the function need to move in sync with shifts in the baseline. Resetting the function now, we can see in a downward vertical shift the same kind of things happen. Instead of adding to our function, however, we can represent this as subtraction. Before we close, I just want to make a quick callback to a previous lesson. I had alluded to the fact that sine waves and cosine waves were kind of hidden in each other. It turns out that it's less about being hidden in one another, and more about cosine and sine actually being the same wave, just out of phase by pi over 2 radians. As you dive into calculus, you're going to discover way deeper and more interesting connections between sine and cosine. But until then, feel free to leave me any comments, questions, or concerns.